Hello, ladies and gentlemen. My name is Joshua Olusegun Ajetomobi. It's my pleasure to welcome you to this free webinar on basic econometrics using R, part 2. I appreciate those people that attended the first part. I'm very grateful for all of us that are present, even for this part 2. God willing, every second Friday of every month, we'll be meeting on this type of free webinar. So let us take notes. Though as usual, we shall continue to send the invitation. Today, we want to look at assumptions of linear regression model. And unlike the first time we met, today we'll be using R Markdown so that we'll not be shifting from PowerPoint or Microsoft Word to R Studio. R Markdown is an authoring framework in our ecosystem. The main advantage is that it helps us to combine the codes, the text, and the output in just one reproducible document. For some of us that are not familiar with R Markdown, to launch it, just go to File, then New File. You will see R Markdown. So you click on R Markdown here. So here you have the title. So just type assumption of a linear regression model. Then you click OK. Then you will have something like what we have on our R Studio. So since I've launched it, let me cancel it here. So let's move forward. Since we want to look at the assumptions, for the sake of people that did not attend the last session, let me quickly remind us some of those things that we considered. We look at fundamental concepts of econometrics. We consider the definition of econometrics, the rationale behind econometrics. We look at the advantages. We look at the functions. We look at the key components of econometrics. Then we look at the basic procedure for econometrics analysis. So we look at simple regression model, and we look at scatter diagram approach to estimating simple regression model. We look at correlation analysis. We look at estimation of simple linear regression using ordinary least square method. And we round up by estimating multiple regression model. So today we are going to begin with the estimation of the multiple linear regression model before we consider the assumptions again. Even last week we looked at assumptions, but we just listed them. But today we are going to test for their validity, because that is a very good way to start your analysis after estimating linear regression model. So let's go to business. As a reminder, the three key components of a regression model are the model coming from our theories that we have expressed in mathematical symbols. Then we collect our data and we estimate the model using appropriate econometrics technique or techniques. So after collecting the data, the next important question is, how do we estimate the model? Ordinary least square is a commonly used approach to estimate a Bayes regression model. So let's fix idea. Let's say we are dealing with 4 variables, 1 dependent represented by y here, and 3 independent, which are x1, x2, and x3, and we assume a linear function. So our y is dependent variable, x1 to x3 are the independent variables, and our e is the residual or the error term. We can rewrite the model in terms of the error. That is what we have in line 19. And we can just write it simply as in line 21. Where y is dependent, then we have our x standing from vectors of the independent variables, that is our x1, x1, x3, and our a standing for vectors of the parameters to be estimated, that is our a0, a1, a2, and a3. So the equation states that the error term is the difference between the actual value of y, that is the observed, and the predicted value, that is the value of y obtained after running our regression model. So one way to obtain the coefficient is to minimize the sum of our error. That is, we are trying to make the residual as small as possible. For theoretical and practical purpose, we do not actually minimize the sum of the error, but the sum of square of the error. Take, for instance, if you are dealing with small samples, definitely you will have some residual negative, some positive. If peradventure you have more negative in terms of magnitude than positive, then you will end up having the sum to be negative. So to avoid maybe looking at which negative is higher in terms of the summation or not or so on, that is why it is always better to use the sum of square, because the moment you are using the sum of square of the error term, you are dealing with positive values throughout. So in line 23, this is stating the sum of square of the error function. So let us call the sum of the square error ESS. So after collecting the data, we have values for y, we have value for our x's, but we don't have value for our E0 to E3. So to find the A coefficients, that is A0, A1, A2, and A3, we need to minimize the error sum of square, the ESS. And we want to do that, then we begin with the first order condition by equating the partial derivatives with respect to each of the A coefficients to 0. And we solve the simultaneous linear equation. We are not doing that manually. So this is what we'll be using our software to solve, so that we'll be able to obtain all the 3 regression coefficients as well as the intercepts. Let us not forget the estimation we are carrying out is actually based on sample data collected from a population. So our estimated model is called sample linear regression model, as a representation of the population linear regression model. So it's clear to us that our population regression model, we have error terms. So let us call that one y. The sample regression model, let's call that one y hat, in which case we will be handling the error term by looking at the validity of the assumptions. So the difference between the y and the y hat is actually the residual. So the y hat is called the estimator, of our AX, and the A coefficients are the estimators of the population coefficients, while the E, that is the difference between our Y and the Y hat, is the residual. The numerical value of an estimator is called an estimate. We should take note that the estimator and the A coefficients are random values because their value will change from sample to sample, as I've said earlier. So they are the best guess of the population parameters. So to find out whether the sample linear regression model is close to the population linear regression model, we need to understand the assumptions of the regression model and test for their validity using R. And that is exactly what we want to do today. So we'll be considering the assumptions one after the other and testing for their validity. So we begin with linearity assumption. So the model assumes linearity in the parameters. Let us pay attention to linearity in the parameters. As shown in our equation above, that is, we have our y equals to a0 plus a1, x1 plus a2, x2, and so on. It may or may not be linear in the y and x variables. The ordinary least square can see and do nonlinear relationship between the variables if transformed in a way that preserves linearity in parameters. Take, for instance, if we are considering quadratic equation, we have our y as a0 plus a1 x1 plus a2 x1 squared. That one is x1 raised to power 2. So that's x1, okay, raised to power 2, plus the other term. So you can see that the parameters are still in linear form. So we can still solve it using the OLS approach. So the linearity assumption can be tested using any of the following three approaches. We have the residual plot approach. We have component plus residual plot method, then we have reset method. So let's take them after the other. So the residual plot. The residual plot is the plot of the fitted values against the residuals. And the R code is, after estimating the model, let's call it model, just a plot, which equals to 1. The first graph that we come up is always the graph of the fitted values against the residuals. And you just check the graph visually. If the observations show random scatter points around the red line, then linearity and constant variance holds. If it shows a curve pattern or systematic waves, then the linearity assumption is violated. A funnel shape, that is, with increasing or decreasing spread, indicates heteroscedasticity. We are coming to that. So today we want to use one of the data sets in R. So we need this package, Cable Extra, so that we can generate a kind of table that we need in Microsoft Word. Excuse me. So we have our library Cable Extra. We have our data long list. Since the data list in R, that is, as you install your R and R Studio, the data is already there. So in order to load the data, just type data, then you put the name in quotes. So to look at the data, the first 6 observations, that's why it's head means the first 6, tail means the last 6. So, and you can run the chunk. This is the way to run the chunk. Just come here, that is run current chunk. So just click on it. Yeah, so after running it, you will see the result here, simple CBC. So the variables are GNP deflator as a measure of inflation. We have GNP. We have population of unemployed, population of people in armed forces, the entire population, then the year, then we have population of those that are employed. So, and that is the last 6 observation. So let's run the regression model. To run the regression model, we are introducing model summary package so that we can generate publication ready table after estimating the model. So to estimate the model, we want to look at employed as the dependent variable, that is number of people employed. So maybe it's a kind of looking at labor force participation model. So if you want to include all the other variables as independent, then you don't need to list them. That's one beauty of R. Just a point, comma, then you define your data. So then if you just run this and you say model summary model without defining the name of the model, it's going to write 1 there as the title for the dependent. But if you want employed to be the title, just type or define it, list. This is the name equals to this model. Very, very straightforward. And then you can now say model summary, model 1. The essence of this is to ensure that the label for the model is employed and not 1, because it's not just going to put 1 there if you don't do this. Or you can actually do that in since it's going to produce the results in publication ready in Microsoft Word, and type your employee there if you don't want to follow this approach. But I think this is still a very limited number of codes. That's fine. So run the chunk. So if you run the chunk, you will get this. So you have the intercept and you have the star showing the level of significance. So you have GNP deflator insignificant, GNP insignificant, unemployed significant, armed forces significant. Then you have population insignificant. You have year as the trend significant. So, and you have your R squared, adjusted R squared. You have your archaic information criteria, variation information criteria. Then log likelihood. You have your F statistics, root mean, standard error. So most of the time, researchers and students and researchers are always eager to explain these results, even without performing the diagnostic test. That is not good. That is not proper, because all these results might be due to sampling error. So we really want, because if you take another sample, are you sure it's a representative of the population? Because what we have here is the sample regression model. So in essence, you have to ensure that you test for validity of the assumptions before you begin to explain the coefficients. And that is exactly what we want to do. So let's test for linearity, because we have estimated the linear function. So the residual plot, after estimating, just say plot is the model, which is equal to 1. So then you have this kind of graph, this graph of residual versus fitted. And you can see that the point are scattered all over. So, and that shows that linearity assumption is not validated. Another way to test for linearity, if you don't want to use the residual plot, is to use component and residual plot approach. So the component and residual plot shows a blue straight line, that is the OLS linear fit, and a red smooth curve, that's not parametric smooth fit. and some dots, that's partial residuals, adjusted for other predictors. So the linearity assumption was if both lines are very close, that is the red line and the blue line. So the function is component residual CR plots. It's in car package. So we have library car, then CR plot model. So after estimating it, this is what we have. You can see that the line and the blue line, they're very, very close. So confirming that the linearity assumption is not validated. This is easier to read than the residual plots. Another approach is to use Ramsey regression specification error test. The reset test is used to test for general misspecification. It's often used to detect non-linearity. And what you are looking for is if the p-value is less than 0.05, less or equal to. And that would suggest that the model may have been misspecified, potentially due to non-linearity, omitted variables, or incorrect functional form. So it's in LM test package. So this reset test, then your model. Then if you have done it, you will have this result. What you are looking for is this p-value. And this p-value is greater than 0.05, which means there is no misspecification. That is, the linearity assumption is not actually validated. So, which means the relationship can be approximated with a linear model. And that takes us to the second assumption, exogeneity assumption. The error time and independent variables are assumed to be independently distributed. In practice, this assumption is tested indirectly because the true error time is unobservable. Because error time actually accounts for vectors of other variables that you have not included in your model, so it's not observed. We only observe the residuals after estimating the model. So when the error time and our independent variable is the full mixes of all independent variables for all observations. E stands for the expected value. Hence, the expected value of the error time given the vector of independent variables is 0. That is, there shouldn't be any meaningful correlation between our X and the error time. A serious violation of this assumption means that our OLS estimates will become biased and inconsistent. And that suggests the presence of endogeneity, often due to simultaneous causality, omitted variables, and or measurement errors. And to test for this exogeneity, we use Dobin-Wool-Osman test. So detecting exogeneity, or more precisely testing for endogeneity, which is the violation of exogeneity in R, is typically done using the Osman test, especially in the context of instrument variables regression. So what we normally do is we run the OLS, then we run the instrument for regression, and we look at whether they differ significantly. And if that is the case, then endogeneity is likely. If not, the variables can be treated as exogenous. So in our example, we may wish to test whether unemployed is endogenous, that is correlated with the error time. So we can use the Osman test in that. So let's look at step by step to test for exogeneity in our model. The first step is we run our model as usual. So this running our model. So we've done that before. This is our results. So step 2, you choose an instrument if an independent variable is endogenous. So assuming that unemployed is endogenous, so we have to have an instrument to control for the endogeneity. Suppose unemployed is endogenous. For example, higher unemployment reduces the number of people employed. So we need an instrument for unemployed. And that variable should be correlated with unemployed. That is the first thing we are going to test with. That is relevance. So it should affect employed only through its effect on unemployed. So the instrument must be strongly correlated with the potential endogenous variables, e.g., let's say inflation, that is GNP deflator. So we can test the relationship by running a simple regression of the variable against the unemployed. So let us assume that GNP deflator can only affect employed through unemployed. That is an assumption. So our first thing to do is we run a simple regression of unemployed against the GNP deflator to check whether it actually affects unemployed. Don't forget, in the previous equation, we have included both as we treated both as exogenous. So let us look at the relationship. So in this case, you can see that GNP deflator actually affects unemployed positively. So in terms of relevance, it suggests that it could actually be an instrument. Now that GNP deflator influences unemployed, but not employed directly, we can proceed with the instrument form model. So if weak instruments, F statistics will be greater than 10. So we are looking at F statistics value. That is what we are going to check, whether it's greater than 10 or it's lower than 10. And the procedure to carry out the instrument for is what we have here. So we have the for reg function is in AER package. So let's run for model. This is our model. So in this case, we have employed as a function of GNP, unemployed, armed forces, population, and so on. So believing that unemployed is endogenous, so we try to, you can see this perpendicular. We will repeat what we have here, say GNP, but we now replace this unemployed with the instrumental variable, GNP deflator, and include all the other variables in our data. Then we run the summary and the diagnostic test. If you have done this, you can run the chunk here. So let's look at the results. Yeah, so this is our results. So you can see that unemployed significantly affects employed, armed forces also, as well as year. So, but before you begin to explain, you have to look at whether the instrument is weak or not. And like I told you, you just check these statistics. If it's less than 10, it is weak. You can even check the p-value. You can see it's a weak instrument. We are looking for a value that is greater than 10 here. It's a weak instrument. So since it's a weak instrument, my advice is always try to look for a better instrument, very strong one. Yeah, getting a reliable instrument is always somehow, it's always the problem when you are dealing with instrumental for regression model. So in the result of the diagnostic test, the F test is less than 10, which implies that GNP is a weak instrument. The Wolfman test p-value is greater than 5. This implies that endogeneity may not be as serious as we imagine, but we still have to look at this rule of getting a very good instrument. That is that. You may try some other instruments based on the equation that we have, based on the data that we have. If the linearity assumption of OLS is violated, that is, the relation between the dependent variables and the dependent variable is not linear, there are various approaches to address this issue. And some of the solution to deal with the violation, one, you can transform either the dependent or independent variable. So you can use another functional form. The second approach is to apply smoothing techniques such as generalized additive model and locally weighted scatter plot smoothing. If the non-linearity can be traced to interaction between the independent variables, then we can introduce interaction terms in the model. So you can have your regression with interaction terms. So these are some of those things we'll be doing in our next class. So we'll be looking at various functional forms and various ways through which we can bypass some of these econometric problems. So another approach would be the use of nonlinear and machine learning models. So we move to the third assumptions of linear regression, independence of the error term. Another key assumption of the OLS is that the error terms are independently related. So if the error terms are not independent, that is, if they are correlated, it violates the assumption that each observation is giving new independent information. So in time series, we call this autocorrelation. In clustered or panel data, it is time group level correlation. While in spatial data, it's called location-based dependence. So if violated, the OLS coefficient will still be unbiased, but the standard error will be wrong, leading to invalid p-values and confidence intervals. Hence, the significance level will be overstated. And one way to test for autocorrelation is the use of W-Watson statistics, which ranges from 0 to 4. So if the value is around 2, it shows no autocorrelation. When it's less than 2, it means positive autocorrelation. And when it is greater than 2, it means negative autocorrelation. So the function DW test is in LM test. So let's run it. So if you look at our value, that's 2.56. So in our example, the W-Watson is 2.56, which is greater than 2, which implies negative autocorrelation. So if violated, the solution includes the use of lagged variables. So in our situation, we may include the lag of the dependent variables in our model. So another approach is to use Cochrane-Court procedure, New West robust standard error, and or estimate time series models. There are quite a lot of time series models that can be used. And that takes us to another assumption, which is normality assumption. The normality assumption in regression model refers to the distribution of the error terms. Please take note, distribution of the error terms, not the variables themselves. It means that your error term is normally distributed with means of 0 and constant variance. So the assumption is needed to test the validity of the T and our F statistics as well as the confidence interval, particularly when the sample size is small. For a very large sample size, maybe from 200 and above, it may not be a serious problem. So to test, we can use histogram of the residual and check whether we have bell shape. We have QQ plot approach. We have Shapiro-Wilk test of the residual, and Darling, Lilly Force, or Kolmogorov-Smirnov, as well as Jackie-Berra test. So let's try to use our example. If the assumption is violated, you can use robust standard error, you can bootstrap, you can transform the dependent variable, you can remove outliers, you can use generalized linear model, or if it's possible, just simply increase the sample size. So let's start with plotting the histogram. So to plot the histogram, we have our compound. We use a function, plot normal histogram, in our companion package. So don't forget, we are drawing the histogram for the residual. So I use brown color, and I say the line color should be blue. So if you have done that, you can run the chunk. You already know how to run the chunk. So then you have this. So this is almost a bell shape, which is showing that the normality assumption is not violated. So the figure shows that this histogram is approximately normal. So the distribution of the error term is symmetric around the mean, which means that the normality assumption is not violated. So we have the QQ plot test, which compare the distribution of the residual to a perfect normal distribution. So we are looking for the dots that fall in a straight line. So if they are not, then the normality assumption is violated. So let's look at that. And to do that, plot the model, which is equal to 1, to 2, which is equal to 1 will give us residual versus fitted value, which we have done before. So this is the QQ residual. You can see that many of the points actually fall on the line, even those that are not, some of them are very close. So this is actually showing us that the normality assumption is not violated. So we have Shapiro-Wilk test for normality. OLS assumes the residual are normally distributed, especially if the sample size is small. The Shapiro-Wilk test helps us to check if the assumption holds. So the code is Shapiro.test, that's the function, and receipt standing for the residual. This the model that we have estimated. So if the p-value is greater than 0.05, then the normality assumption is not violated. So this is what we have. And in our own case, we have it to be 0.47, which is far above 0.05. So which means the normality assumption is not violated. We have Anderson-Darling test. Just like Shapiro test also, the way we carry out the test is almost the same. But this test is more sensitive in the case of the distribution than the Shapiro-Wilk test. So it pays extra attention to whether you have too many extreme values, that is outliers. So the function is in not test package. So we have ad.test. So and if you have done it, again, our interest is this p-value. So the p-value is also far greater than 0.05. So which means the normality assumption is not violated. Then we have Kolmogorov-Smirnov. It's a classic goodness of fit test. But when used for normality, it has a few distinctive features, both strengths and weaknesses. It compares the residual distribution to a theoretical normal distribution and calculates the maximum difference between the residual's cumulative distribution and the normal distribution. So it's a weak test. So, but to do it, it's Lilly.test. It's also in not test package. So, and again, you check for the p-value. In our situation is 0.23, which is far above 0.05. And that takes us to the last one, which is Jackie-Berra. Jackie-Berra test is unique because it checks if the residual from regression are normally distributed by testing the skewness and kurtosis. So, and it's in T-series package, so Jackie-Berra test. So again, we check for the results, and our interest is the p-value. The p-value in this case is 0.71, which is far above 0.05. So all the tests confirm that normality assumption is not violated in the model that we have estimated. Now to homoscedasticity. Another important assumption of the OLS is that the variance of each error term, given the value of the independent variables, is constant. That is, the error term is homoscedastic. Homo means equal, scedastic means variance. So in simple terms, as the predicted values increase or decrease, the spread of the error term stays the same. The valuation is what is called heteroscedasticity, and the standard errors will be wrong. the t-test and the p-values may be misleading, and the confidence intervals may be too narrow or too wide. There are various techniques to test for homoscedasticity. This includes plotting the residual, I said it earlier, Brush-Pagan, Godfred quants, use of non-constant variance curve, and spread level plots. The solution to violation of the assumptions include the use of robust standard error, weighted least square method, transformation of the variables, bootstrapping, model specification, and lots more. So the residual plots, if it gives us Funnel shape, then it shows heteroscedasticity. So in our example, you can see that it's scattered all over. So it's not giving us funnel shape. So the ideal of heteroscedasticity is not just there. So the assumptions of homoscedasticity is not validated. Let's use Brush-Pagan. So plot is in LM test, BP test, our model. So this is the result. Again, we are looking for the p-value. So this p-value is less than 0, is far greater, than 0.05, which means that homoscedasticity assumption is not validated. And again, for Godfred quint tests, so again, is GQ test is in LM test. And again, what we are looking for is the p-value, in this case 0.21, and is greater than 0.05, which means homoscedasticity assumption is not validated. We have the non-constant variance approach, NCV, to show whether the variance of the residual is related to the fitted values. So the p-value is in CAP package, it's NCV test. You can see the p-value is 0.87, which is far above 0.05. And the last one is spread level plots to check whether the residual from the regression model have constant variance. So again, you can read through. It's in CAP package, so we have spread level plots. Again, what you are looking for is a clear distance between this dotted line and the graph. So in all that we've done, we can see that homoscedasticity assumption is not validated. So we don't have problem of heteroscedasticity. And that takes us to another assumption, multicollinearity. Multicollinearity occurs when two or more independent variables are highly correlated with each other in the regression model. In simple terms, it means the predictor that these independent variables are providing overlapping or redundant information. So multicollinearity does not affect overall model fits like R-square, but it causes issues such as inflated standard errors and unstable coefficient, which makes it unclear how much each variable really contributes. So there are various methods for detecting multicollinearity. You can carry out the correlation analysis, trying to obtain the correlation matrix. We have variance inflation factor approach, eigenvalue value like conditional number, tolerance, determinant of the correlation matrix, and the use of auxiliary regression. So let's start. Correlation matrix is the pairwise correlation between multiple numeric variables. So each cell in the matrix contains correlation coefficients. The value range from -1 to +1. +1 means perfect positive correlation, -1 perfect negative correlation, and 0 means no correlation. So multicollinearity is suggested if the correlation coefficient is greater than 0.77. If the assumption is validated, the solution includes removal or combination of highly correlated predictors, the use of principal component analysis in order to get maybe a kind of index, or to have reduced number of variables. We have partial least square method, ridge regression approach, standardization of the predictors, and removal of what is called dummy variable traps. So to obtain our correlation matrix, we use cut-plot package. We run the correlation as COR for the variables. Then we have the plots. Then if we have done so, this is what we are going to obtain. If you look at it now, you can see between GNP and GNP deflator, the correlation is very high, 0.99. You look at population and GNP deflator, 0.98. Population and GNP, 0.99. Year and GNP deflator, 0.99, and so on. So we can see clearly that there's a problem of multicollinearity here. So another method is to use variance inflation factor. VIF measures how much the variance of regression coefficient is inflated due to multicollinearity. So when one independent variable is correlated with others. In other words, VIF tells how much a predictor is explained by the other predictors in the model. So it's 1 divided by 1 minus R squared. So if you look at our example, just it's in car package, so just type VIF model. So you can see what we are looking for is value less or equal to 5. Here we get 135, 1,788, 33. Here we have 399, 758. Apart from one that is 3.58, all the other variables, all the other ones exhibit multicollinearity problem, serious one. Eigenvalue and conditional number. So in this case, we compute the eigenvalues of the transport of x and x. So the eigenvalue tells us about the spread of variability in different direction of the data. So if one or more eigenvalues are very small, that is very close to 0, it suggests that the predictors are mostly linear combination of others. So we signal multicollinearity. So, and when the conditional number is less than 10, it means there is no problem of multicollinearity. A value between 10 and 30 means moderate multicollinearity. Value above 30 means there is serious problem. So let's look at our example. The function is kappa. It's in base R, the model. Look at the value. Imagine we are looking for value less than 30. Here we get, this is almost 22 million plus. So this is serious problems of multicollinearity. Tolerance is the reciprocal of variance inflation factor plus 1 over it. So a low indicates multicollinearity. So, and let's look at, it's in OLS RR package. So, and this is OLS VIF underscore tall model. That's the function. So, and look at the results. So you can see lower than 0.2, lower than 0.2, lower than 0.2. So only the value for armed forces is greater than 0.2. So, and that is the only one that could be said not to have problems of multicollinearity. Again, we can look at determinant of the correlation matrix. So after obtaining the correlation matrix, you can get the determinant. If the determinant is large, close to 1, it indicates that the predictors are uncorrelated or weakly correlated. If it's close to 0, it suggests that the predictors are highly linear dependent. that is collinear. When independent is near zero, the data is nearly singular, meaning that some of the independent variables can be expressed as linear combinations of the others. So you can see it's very close to zero, because this is 0.0000, because this is 7.14 multiplied by 10 to the power minus 11. And this is showing us clearly that we have very serious problems of multicollinearity in our long-lived data sets. Another method is use of auxiliary regression. Auxiliary regression is a secondary regression analysis used to check for multicollinearity, especially in the context of the variance inflation factor and other diagnostic tests. It's essentially a regression of one independent variable on all the other independent variables in the model. So this helps determine how much of the variance in one is explained by the other. So our interest in this case is to check for the adjusted R square after running regression of one independent against all the other independent variables. So you know employed is our dependent. That is the only one that will be left out. So in the first one, we run GMP against all the other. The second one, we run GMP deflated against all the other variables. We run unemployed as a function of the others, armed forces as a function of the others, population as a function of the other. Yeah, so we just pick one variable, then run it again. So we use this OLS list or whatever in order to obtain just one table. We have model summary OLS that we have defined. Then we ask it to star all the variables that are significant. That's exactly what we've done. So let's run the chunk. Yeah, you can run the chunk. So good. So let's look at the results. So this is the results. So you are looking for the adjusted R square. You can see 0.99, 0.9, 0. So 0.99. So apart from this, maybe let me check the dependent here. Apart from armed forces, and we have even discovered that armed forces is okay. All the other ones, you can see the adjusted R square is very, very high. All the others are greater than 0.7, you can see. So now we have seen that we have very serious problems of multicollinearity, and I've told us what we can do, and that will take us to what we'll be doing next in our next class. So again, thank you very much. I appreciate your coming, and please take time to go over this video over and over again, particularly to get yourself familiar with all these assumptions of linear regression and how to test for their validity. And in case you have some questions, you can contact info@jaeqm.com, and definitely I will respond to your comments, or you can contact me on my WhatsApp. So again, thank you very much. I appreciate your comment. Thank you, and thank you until we meet again. I'm Joshua Shepherd, See you again.